In this next video on our series of Laplace transforms, we're going to compute the inverse Laplace transform of a whole bunch of different functions. But before I start, I want to introduce a property of the Laplace transform called the translation property that's going to be very helpful when it comes time to do inverse Laplace transforms. I want to begin by presuming that I have the Laplace transform of some function. That is, I'm going to compute the Laplace transform of a little f of t, and suppose that this is going to be some big F of s. Indeed, our assumptions that this Laplace transform was always going to exist if, for instance, the f of t was of exponential order. We've seen that in a previous video. So what I want to do now is investigate not the Laplace transform of f, but the Laplace transform of e to the at times f of t. That is, I want to know what happens when I multiply by some exponential. Now, by definition, this Laplace transform is defined to be, well, the integral from 0 up to infinity of e to the minus st times whatever I'm taking the Laplace transform of. In this case, it's e to the at times f of t, and then all of that is integrated with respect to t. I am going to quickly observe here that I have two different exponentials. And so I could surely put those together and just say that this is the integral from 0 to infinity now of e to the minus, instead of st, it's s minus a times t, and then f of t dt. Note that there's two minus signs in front of the a, which gives a positive in front of the a. Now, what's nice about this expression is that because I have combined the e to the minus st and the e to the at together, it looks like one exponential with a coefficient of s minus a. And as a result, the expression that I have looks a lot like the Laplace transform of the original function f. The only major difference is that opposed to having an e to the minus st, I have an e to the minus s minus at. And as a result of this, what I have is just the normal Laplace transform, the capital F, but instead of f of big S, it is now f of s minus a. In other words, what I have come up with is this translation property that the Laplace transform of an exponential times a function is just the same thing as the Laplace transform, but translated. That it's no longer at f of s, it's at the value of s minus a. So this is referred to as the translation property of the Laplace transform. All right, so let's see how we can use this in some examples. All right, so let's use this property. I want to do, as an example, the inverse Laplace transform of something, and I'll give some expression here, and I'm going to give this particular expression 2 divided by s plus 1 cubed. And so my goal here is to compute the inverse Laplace transform of this particular function. Now, when you're computing the inverse Laplace transform, it's a little bit like finding the antiderivative of a function. If you know what a lot of the standard derivatives are, you can undo those standard derivatives when you go and try to find antiderivatives. The same kind of analogy applies here. If you want to find an inverse Laplace transform, what we need to do is have a sort of repository of standard functions that we know what their Laplace transform is. And therefore, when you get some new expression like 2 divided by s plus 1 cubed, you try to interpret that as looking something like one of the ones you already know. And so the Laplace transform that I think is most relevant to know that applies in this case is the Laplace transform of t to the n. And we've previously seen that this is just the same thing as n factorial divided by s to the power of n plus 1. So they look a little bit similar. There's a sort of a s plus 1 cube thing going on. Now, if I look back at this 2 over s plus 1 cubed, the thing I want to take the Laplace transform of, it looks a lot like this answer of n factorial over s to the n plus 1, perhaps with n equal to 2. Except that there's this s plus 1 down here. In other words, I have a translation, so it's no longer a function of s, it's a function of s minus a, and in this case, the value of a appears to be minus 1 because it's s plus 1, so s minus 1. And as a result of that, if I want to get to the final answer, well, I note that 2 factorial, if n was 2 factorial is just going to give me 2, which is what I have on the top. And so this looks to be just an e to the minus t, that's coming from up here, the e to the at, that I get from the translation. And then I'm going to multiply that by t squared Reason why it's squared is because if n is equal to 2, then this is going to result in the division by s cubed, which is what I have. And then since on the top I have this 2 factorial matching, everything aligns. So this is how I was able to compute the Laplace transform by taking the shift. But let's see another example. In this example, we're taking the Laplace transform, not the inverse Laplace transform, but nevertheless, it is an exponential multiplied to something that we've previously seen, and thus we can apply the translation property again. That is, I'm going to write down what the Laplace transform of sine is, and then shift that value by the value of a. Indeed, the Laplace transform of just sine of kt by itself is just k over s squared plus k squared, and this is valid in the domain where s is greater than 0. So this is a previous fact that I'm going to assert here. And so what's new with this example is trying to deal with the same thing, but with the exponential shift. And so what I'm going to get by the translation property is k divided by s minus a squared plus k squared. And then in this case, I'm demanding that s minus a needs to be greater than 0. That's where this would be valid. But as a result, s minus a being greater than 0 is the same thing as saying that s is greater than a. All right, let's use that in another example. This time I'll go the other way around. I'll do the inverse Laplace transform, and I'm going to do it of s divided out by s squared minus 2s plus 5. Now, the challenge that presents itself right now is that this expression doesn't look anything at all like any of the Laplace transforms we've seen in the past. So there's not an obvious way that I can take this and align with it being some sort of shifted exponential or shifted sign. I need to do a bit of algebra before I can do that. So one of the pieces of algebra I can do is if I look in the denominator, this is an irreducible quadratic. It means I can't factor it nicely. If you try to go and run the quadratic formula, you're going to find that you're going to get complex roots. So I can't factor the denominator. However, the other piece of algebra that I can do to this quadratic is I could complete the square of the denominator. And the reason we're going to do this actually relates to the previous example I had just done, where I see expressions of the form k divided by s minus a squared plus k squared. I want to massage this to look a little bit like that, and so I'm going to do this method of completing the square. But let me remind you how that works. Okay, so let me just look at the inside, the s squared minus 2s plus 5. And my goal here is to complete the square on the bottom. So I may as well just come along and write the top and not touch it. That's not my goal. The way this works is that I want to focus on the coefficient of the linear term, this minus 2. I divide that by a half. This is going to give me the value of minus 1. And then what I want to try to write this is as s minus 1 squared. Now, if I had done that, the first two things align, so s squared, and then there's going to be a minus 2s, but then there's also going to be a plus 1. And as a result of that, I need to have a plus 1 stolen in some sense from the plus 5 that was there. And as a result, what I am left with is just the value of plus 4, and I'm actually going to write 4 as 2 squared to make it a little bit compatible with the k squareds that we've seen previously when we take, for example, the Laplace transform of sine or cosine. Now, this is okay, except I'm now going to look up in the numerator. I have an s in the numerator, which sort of is in contrast to the s minus 1 that's down in the denominator. So the other thing that I'm going to do is I'm going to write the top as s minus 1 plus 1. So I can sort of isolate away the s minus 1. Again, I'm not doing anything. And then on the denominator, it's s minus 1 squared plus the 2 squared. Final thing in this sort of thrust is to write this as s minus 1 divided by s minus 1 squared plus 2 squared. And then finally, plus 1 divided by s minus 1 squared plus 2 squared. And so with a little bit of foresight as to where I'm going with this problem, I know that these are going to look a little bit like sines and cosines, or at least translated versions of sines and cosines. For instance, I will remind you that the Laplace transform of sine of kt is going to just be k divided by s squared plus k squared, while the Laplace transform of cosine of kt is equal to s divided by s squared plus k squared. So now if we return to the way in which I wrote it, the first expression, well, it looks a lot like the cosine of 2t expression does. The only difference is that instead of having an s everywhere, there's an s minus 1. And then for the second expression, it looks a lot like the sine term, except instead of a 2 on the top, which would be what it would be if it was the Laplace transform of sine of 2t, there's just going to be a 1. Okay, so how do I manipulate this? So while I had only done algebra before, now I actually will come along and take the inverse Laplace transform of this expression that I've now developed. So this is the s minus 1 divided by s minus 1 squared plus 2 squared. That's the first expression. And then 1 over s minus 1 squared plus 2 squared. A lot of copying and pasting there. Nevertheless, okay, so if I focus on the first term, well, that sure looks a lot like this cosine that I have here. It's just that it's a cosine that has been shifted because instead of an s appearing, there's an s minus 1 everywhere. The way that I deal with shifts is to say that this is going to be e to the t. And that the way I deal with the rest of it is I just say that this is going to be a cosine, and specifically it is a cosine of 2t. As for the second term here, well, that second term is going to look a lot like a sine, except I'm supposed to have, if it's sine kt, I have to have a k on the top. So in this case, I should have a 2 on the top. I do not have a 2 on the top. And that's okay. I can just come here and say that this is 1/2 of putting a 2 on the top, unless it is 1/2 of sine of 2t. And so that is now my final answer. So in this video, I hope we've gained a little bit of practice of taking either the Laplace transform of a function or perhaps even more interestingly, the inverse Laplace transform of a function. And then we've seen that when we're doing these inverse Laplace transforms, one of the things that we want to try to do is apply algebraic tricks like the completing the square that we did here to make what we are given with just look like something that we know before or something that we know before together with a translation. So in this last example, we had seen that it was just a sine and a cosine term, but they had both been shifted by this exponential, this e to the t.